Welcome, everyone. Ready to dive deep into deep learning? We're tackling the book Deep Learning, Foundations and Concepts today.
Yeah, it's a fantastic resource, great for beginners,
Yeah.
but even if you've got some experience, it really solidifies those core ideas.
And what I love is how it's not just theory. They actually bring in these real-world examples.
Absolutely. Like right away in chapter 1, the deep learning revolution, they talk about how deep learning's being used to diagnose skin cancer from images.
So powerful, right? Seeing that practical application right off the bat.
Really highlights supervised learning, training a model with labeled data, in this case, those skin lesion images and whether they're cancerous or not.
Again, the chapter breaks down supervised learning nicely, like what's classification, what's regression.
Yeah, classification's all about categorizing. Is this thing A or B, like with the skin lesion benign or malignant? Regression, though, that's predicting a specific value, like, say, how much yield you'd get in a chemical process.
Can't forget about those large language models, the LLMs.
Ah, yes, the heart of all this generative AI buzz.
They can do some seriously impressive things, like writing text that's indistinguishable from human-written stuff.
And chapter 1 doesn't shy away from the tricky parts either. They address overfitting, which is when your model gets a little too good at learning the training data.
So it ends up failing when it sees new data.
Exactly. They use a great analogy, fitting a curve to some data points.
Right.
If your curve's too complex, it nails the training data, but then totally bombs on anything new.
And their solution? Cross-validation.
Like a practice test for your model.
Love that. And the chapter wraps up with single-layer networks, a little history lesson on the perceptron model.
Which paved the way for all the complex deep learning stuff we have today. Then we jump into chapter 2, probability and information theory.
Sounds daunting, but the book makes it pretty digestible.
It starts with the basics, like the sum rule, product rule, those fundamental probability concepts.
And then Bayes' theorem makes an appearance.
Which, let's be honest, can be tough to grasp. But they use this fantastic cancer screening example, makes it crystal clear.
And that leads into prior and posterior probabilities. Key to understanding Bayesian inference.
Chapter also covers some important statistical ideas like expectation and covariance, which help us describe those random variables.
Oh, and we can't forget our old friend, the Gaussian distribution.
Always popping up. But it's so important because it has these properties that make it relevant in so many different areas.
The chapter finishes by showing how all this ties into machine learning, how that Bayesian inference is a powerful tool for learning from data.
Then chapter 3 takes us on a tour of standard distributions. Those are like the building blocks for probabilistic models.
Starts with the Bernoulli and multi-Newly distributions, for events with distinct outcomes, flipping a coin, rolling a dice, that sort of thing.
Then they get into sufficient statistics, which are like concise summaries of your data. They capture all the crucial info for a specific distribution.
We also revisit the Gaussian distribution, but this time it's the multivariate form.
Gotta handle that multidimensional data. The chapter also introduces conjugate priors, which are super handy in Bayesian inference.
And we get a rundown of other important distributions. The student's t-distribution, the gamma distribution, the von Mises distribution, each one with its unique uses.
They wrap it up with non-parametric density estimation,
which lets us estimate those probability distributions without having to make strict assumptions about their shape.
Then we move into the real meat of building and training these models. Chapter 4 is single-layer networks, regression.
All about predicting a continuous target variable using those input features.
They introduce linear regression models, simple but effective, and discuss how to beef them up with nonlinear basis functions.
Got to capture those complex relationships in the data.
Back to decision theory and expected loss, too, with a focus on squared loss in regression.
They also explain this crucial trade-off: bias versus variance, fundamental concept in machine learning.
Bias is the error you get from simplifying the real-world problem into a model.
And variance is how sensitive your model is to those little changes in the training data.
Getting that balance right is crucial.
And they illustrate it all using polynomial curve fitting. Shows the bias-variance trade-off and how regularization helps us control model complexity so we don't overfit.
Chapter 5 switches gears to single-layer networks, classification. Now we're assigning data points to specific categories.
Right, so not predicting a value, but saying this belongs to group A, this to group B, and so on.
They start with defining classification, introduce those linear discriminant functions and decision boundaries. Helps us visualize how classification works.
Then they explain the least squares approach to classification, drawing parallels to the linear regression we saw earlier.
Back to decision theory again, but this time focusing on stuff specific to classification. False positives, false negatives, the RAC curve.
Yeah, all those tools to evaluate how well our classifier is doing.
They compare two approaches to classification, discriminative and generative, highlighting the different ways we can tackle these problems.
And finally, they explore Gaussian class conditional densities, which can lead to those linear decision boundaries when combined with Bayes' theorem. That's a lot, even for just the first 5 chapters.
And we haven't even gotten to deep neural networks yet. Buckle up, because things are about to get even more interesting. And now we're diving headfirst into deep learning with Chapter 6, Deep Neural Networks.
This is where things get really exciting. We're moving beyond those single-layer networks into the more powerful stuff.
Right, the stuff that's really revolutionized the field. But they start by laying out the limitations of those simpler networks, especially when you're dealing with tons of data, those complex relationships.
Yeah, those nonlinear relationships.
They introduce this idea of data manifolds, lower dimensional structures hiding within all that high-dimensional data.
Like, imagine all the pixels in a facial image.
Thousands of them.
Right.
But the real variation, the features, expressions, lighting, that can be captured in a much smaller space.
Makes sense. So then they describe feed-forward networks, information flowing through all those layers of interconnected nodes, and of course, backpropagation.
Ah, yes, backpropagation, that ingenious algorithm, makes training these deep networks actually possible.
It's like a chain reaction, right? Calculating those gradients, updating weights, layer by layer, sending that error signal back through the network.
And they don't sugarcoat it. They talk about the challenges too, like those pesky local minima.
Like getting stuck in a valley, the algorithm can't find its way out.
And weight space symmetries, where you have multiple sets of weights that give you the same output, makes optimization trickier.
Then they explore the different flavors of deep learning. Supervised, unsupervised, transfer learning.
Supervised is what we've been mostly focused on so far. You've got labeled data, you train your model.
Unsupervised, on the other hand, that's when you're working with unlabeled data, trying to find patterns without explicit instructions.
And transfer learning is all about using knowledge from one task to help you with another.
Pretty clever. Then we dig deeper into representation learning, contrastive learning specifically.
All about learning those meaningful features that really capture the essence of your data.
Which can then be used for all sorts of tasks, like classification or regression.
The chapter also talks about choosing the right activation functions. Those introduce the nonlinearities into the network, letting it learn those complex patterns.
And they even touch on inverse problems, trying to figure out the causes from the effects you observe.
Which gets especially tricky with multimodality, where multiple causes can lead to the same outcome.
Then we move on to Chapter 7, Optimization, all about finding those best parameters for our deep learning models.
It's like navigating a landscape, this error surface. The hills and valleys represent different values of the error function, and we're trying to find the lowest point.
That optimal set of parameters.
They explain gradient descent, the basic idea of moving downhill on that error surface.
Following the steepest path down.
They break down batch versus stochastic gradient descent.
Batch uses all the training data at once. Stochastic uses smaller batches.
Stochastic ends up being faster, more adaptable, especially when your data's noisy.
They also stress the importance of picking the right learning rate. You know, how big a step you take with each update.
Too small, you're crawling. Too big, you might overshoot and miss the minimum completely.
They talk about different learning rate schedules too, adjusting it over time for better convergence.
And momentum-based optimization, which helps smooth things out, avoid those oscillations, and speed up the whole process.
Chapter 8 digs deeper into how those gradients are actually calculated, backpropagation, and automatic differentiation.
Those gradients are key. They tell us how to adjust the weights to minimize the error.
They go through the main approaches to evaluating gradients, focusing on automatic differentiation, which has become the go-to technique in deep learning.
It's really powerful and versatile, lets you compute gradients efficiently and accurately.
They explain forward mode and reverse mode automatic differentiation, using a computational graph to visualize the whole thing.
Forward mode calculates as you move forward through the graph. Reverse mode works backward, which is more efficient for those deep networks.
Then they talk about how backpropagation is implemented in practice, using that chain rule of calculus for efficient computation in deep networks.
Essentially, backpropagation's implementing reverse mode automatic differentiation, making it possible to train these massive networks with millions, even billions of parameters.
They wrap it up by touching on the Hessian matrix, which tells you about the curvature of that error surface, gives you more insight into the optimization process.
Chapter 9 shifts focus to regularization, all about techniques to prevent overfitting, making sure your model generalizes well to new data.
So it's not just memorizing the training data, it's actually learning those general patterns.
They introduce inductive bias, the assumptions we build into our models to guide their learning.
Can be through the model design, data augmentation, or regularization terms in the loss function.
They dive into weight decay, a common technique that adds a penalty to the loss function, encourages those weights to stay small.
Keeps the model from relying too much on any single feature, helps it learn a more balanced representation.
They focus on L2 and L1 regularization, explain how they impact the weights, even use visuals to show their effect.
Then they bring in learning curves, plots that show how your performance metrics change over time, helps you monitor training, diagnose overfitting.
They're like a window into how your model is learning, let you spot potential issues.
Early stopping's another simple but effective technique. You stop training when the validation error starts going up, preventing overfitting.
Like a safety net, making sure your model doesn't get too specialized to the training data.
They also cover more advanced techniques like batch normalization, which helps stabilize training, and residual connections, which let those gradients flow more easily through deep networks.
Batch normalizations like hitting the reset button on each layer's activations helps prevent those vanishing or exploding gradients.
And residual connections create shortcuts, letting the gradients bypass certain layers. Makes training those super deep networks possible.
They wrap up with dropout regularization, randomly dropping neurons during training.
Prevents those neurons from relying too much on each other. Forces the network to learn more robust representations.
Chapter 10 takes us into the visual world. Convolutional networks. These have been huge for computer vision image processing.
They're specifically designed for images, right? Take advantage of those spatial relationships and local patterns.
Pixels aren't independent, they're connected to their neighbors. That's where you get those local features that are so important for understanding images.
So they explain convolutional filters, those sliding windows that extract features like edges and textures.
They're like pattern detectors, learning to recognize those specific visual cues.
Then they talk about pooling, which downsamples the feature maps, makes the network more efficient and less sensitive to small variations in the image.
It's like summarizing the information, keeping the key features while reducing the overall size.
They use the VDG16 model as an example, showing how those convolutional and pooling layers are stacked together.
Creates this hierarchy of features, building up from simple patterns to more complex representations.
And they explore ways to actually visualize what those CNNs have learned, like peeking inside their minds, seeing what features they find important.
We can use techniques like feature visualization, occlusion sensitivity, saliency maps, to really understand what's going on inside.
They even touch on adversarial attacks, those carefully crafted images that are designed to fool the network.
Shows how these models can be vulnerable and why robustness is so important.
Then they introduce object detection and localization, not just classifying the object, but actually finding it in the image.
Crucial for so many applications, like self-driving cars or medical imaging.
They explain how sliding windows, implemented efficiently using convolutions, make object detection faster and more scalable.
Chapter 11 takes a turn into structured distributions, exploring graphical models, this powerful way to represent and reason about complex probability distributions.
A visual way to show the relationships between all those variables.
They're great for compactly representing those dependencies and making probabilistic inference more efficient.
Drawing conclusions from uncertain information. They explain the difference between directed and undirected graphical models.
Directed models, like Bayesian networks, show causal relationships. Undirected models just show correlations without implying cause and effect.
They get into conditional independence, a key concept that makes calculations simpler. Certain variables become irrelevant once you know the values of others.
They use some great examples to illustrate this, like the relationship between a car battery, fuel tank, and fuel gauge.
Right. If you know the battery's dead, the fuel gauge reading doesn't matter anymore.
Exactly. Then they introduce the naive Bayes classifier, a simple but surprisingly effective algorithm that leverages conditional independence.
Assumes those features are independent given the class label, simplifies the calculations, but often performs well in practice.
They move on to Markov models and hidden Markov models for handling sequential data like speech or time series.
Markov models assume the current state only depends on the previous one. Hidden Markov models have those hidden states that influence the observed sequence.
They also mention linear dynamical systems, those state space models for analyzing time series and modeling systems that evolve over time.